Don't worry about it. Can you see the screen? I hope that all works. Well, what's wrong with pizza for breakfast? And the recording is on, so we should all be absolutely fine. I think it is just a sort of a convention that you can't have pizza for breakfast, but there's no law in the universe that says you can't. Thank you, Edith. Okay, I need to work more with colors to, appeal to people who have more a sense of aesthetics than I have. Absolutely, absolutely, I fully agree. Yeah, it's. I have to say, we used to have an exchange program for students, an international exchange program with a university in Malaysia. And I worked in Malaysia every now and then. And for me, the highlight was actually the breakfast time, because you could have fried noodles, you could have fried rice, you could have chicken, and nobody would think ill of you if you had some really nice savory breakfast. Well, you don't think about it like that. It's just a nice start, isn't it? And I think, whatever makes people happy in terms of food can't be a bad thing. Okay, shall we get started? Because over the next 3 days, we are going to have quite a bit of ground to cover. And so we have this session today, we have the usual session tomorrow, 9 to 10, and we also have a session on Friday from 2 to 3, just to reiterate that. So, and please don't forget to register your attendance on Moodle, because I think some people have already received some emails from our bioadmin team regarding engagement. And this is something that's really important to us, that students really engage with things. Thank you very much, Bernardo. Excellent. Great that you posted that link again. So what I want to start with you is a little bit of work on acids, bases, pH, and pOH. And one of the reasons that we need to discuss that is because, remember the practical that we did in week 3, where we looked at the absorbance of this paranitrophenol. And I showed you that when we have the paranitrophenol, we get a high absorbance. So we had a high absorbance. But when we added just a little bit of HCl, the absorbance dropped dramatically. Absorbance really went down massively. And that was because we added some acid. But I haven't discussed at that point what is an acid, what is a base, and all these things, and how do these things work. So today, I think this session is predominantly a revision session for most of you, because I think most of you have covered that stuff during A-levels. But hopefully by the end of this session, I will give you a little brain teaser where you will be say, oh, I did not see that coming. Okay, so stay with me and wait for it. So acids, there are basically three different definitions that we can use. One is the definition by Arrhenius. The Arrhenius definition is an acid is any substance that increases the proton concentration, and I write it like that, proton concentration. And very often you see it abbreviated in this square brackets, proton concentration in solution. So that's the original Arrhenius definition for an acid. You are probably all familiar with the Brønsted definition. And because he is Norwegian, you have this O with this line through. Do you remember what the Brønsted definition of an acid is? What is a Brønsted definition? Without Googling. I don't know, Edith. I have no idea. It is actually an acid is, according to Brønsted, is a proton donor. That's absolutely right. And there has also been another definition by a guy called Lewis. And that's slightly different. Leonardo figured it out. Cool. The Lewis definition of an acid is it is an electron pair. And the important thing is pair. Electron pair acceptor. So these are the three most common definitions. And we can look at different compounds, and we can figure out whether they are an acid or the opposite. So you would also have the opposite of things. So a base, which is the opposite of an acid, according to Arrhenius, is a substance that decreases the proton concentration in a solution. Or according to Brønsted, and let's write that down in a different color, base equals proton acceptor. So these are the different definitions. So for example, if we have a compound like hydrochloric acid, HCl, if we dissolve that in water, And HCl is a very strong acid. It almost completely dissociates in water. We would get something like that, H3O plus Cl minus, and this H3O plus, what people usually write, is just simply H2 surrounded by lots of water molecules. Something like that. So there's really a shell around this proton in water, but people commonly write it just simply as H3O plus. So what is HCl? Is HCl an Arrhenius acid? Yeah, so it's Arrhenius. What about Brensted? Is it Brensted acid? So I take that as a yes as well. Now with the Lewis acid, we need a little bit. It's maybe with the Lewis, probably a little bit more careful. And we've got somebody with very heavy breathing. I don't know what you're doing. Yeah, this H3O plus is sometimes also referred to as. No, don't cease your breathing. Please carry on breathing, but maybe you want to mute yourself. It's not healthy to cease breathing. So here's another compound, FeCl3. That's an interesting one because FeCl3 plus what happens with that is something like this. And so FeCl3, what is FeCl3? Is it A? Is it an Arrhenius acid? Does it increase the proton concentration in water, let's say? Yes. So definitely an A. Is it a proton donor? L3. Is it a proton donor? Can it donate a proton? FeCl3. No, because it doesn't have any protons. So it is not a Bronsted acid. But what about a Lewis acid? Now, what we see here is that it accepts an electron pair. The ion accepts the electron pair. And it's the pair that's important. So therefore, it is a Lewis acid. And that's absolutely right, is it? And we will come to that in a minute, that it can donate a proton to something else. But let's stay with that Lewis acid here. The FeCl3 is actually accepting this pair. it does not accept a single electron. If only a single electron, we would talk about reducing or oxidizing. We would talk about this reducing or oxidizing properties for a single electron. But since we are working with a pair of electrons, reducing or oxidizing is something totally irrelevant in this case. Okay, so be aware when we are talking about electron pair acceptors, it has nothing to do with reducing or oxidizing. And that's very important. So let's go back to our hydrochloric acid. So this HCl can donate this proton. So it donates the proton, and we have got the chloride sitting here. And if we dissolve HCl in water, we get lots of these protons in water. And also the chloride ions in water. So this is a proton donor because it can donate this proton. So therefore, it's a typical Bronsted acid. And you are probably all familiar with the concept of we can measure the proton concentration. So we can measure proton concentration. And of course, it is like any other concentration. Proton concentration would be usually given as mole per liter, or we can abbreviate that with capital M. But very often it is much easier to use something slightly different. So what springs to mind when I say measuring the proton concentration in a solution? What would be the keyword be? Yes, exactly. People say pH. Absolutely right. So what on earth is a pH? So pH is just simply defined as, does anyone know? Yes, that's actually a good point. It is, yeah, I come back to that. It is the negative logarithm to the base of 10 of the proton concentration. And let's put that into nice colors here. This is the definition of a pH. pH is the negative concentration, is the negative logarithm of the proton concentration. And very important here, this proton concentration is always given as mole per liter. Very, very important. And you can use this equation as a definition if you like. pH is the negative logarithm of the proton concentration. So, for example, let's, okay, what is the pH range in which a pH can actually happen? And I come back to your question, Bernardo, in a minute. 0 to 14? 0 to 14 is the pH range. Okay. So we have 0, 7, 14. That is what people say, yeah? For the pH range. I come back to that in a minute, Edith, don't worry. So anything that is below 7, this would be called acidic. Anything above 7, obviously, is called basic or alkaline. And 7 would be described as neutral. Okay? So let's do a little bit of calculations and see what we can do with it. Let's say we have a proton concentration. The proton concentration is, say, 0.1 molar. What is the pH? Well, we are coming to the pOH. Don't you worry. Don't you worry. So what's the pH of a 0.1 molar solution? Yeah, it is 0.1 molar. Let's just let's calculate that. We want to calculate negative logarithm of 0.1 bracket equals 1. So the pH in this case is 1. What's the unit of pH? Absolutely right. There are no units. Why are there no units? Bananas. Oh, I'm sorry. Where did I make a mistake? Because it is a logarithm and therefore we cannot use any unit. The logarithm of a unit does simply make no sense. You're absolutely right. Okay, let's say we have a proton concentration of, and pH 1, is that acidic or basic? Acidic, absolutely, because it's in this range. Let's say we have a protein concentration of 1 millimolar. What is the pH? where it says it's 3, 3. Three? Yeah, you're absolutely right. Why is it 3? Because I need to convert that into molar, and 1 milli just simply means 1 times 10 to the minus 3 molar. Okay, so therefore, let's put that in the calculator. So we want negative log of 1e to the power of minus 3. And that's the scientific notation in many calculators. So we should get a pH of 3. pH is 3. Absolutely right. Okay, let's say we have a proton concentration of, let's do 10 molar. Let's do 10 molar. The E is just simply on calculators, the symbol that it is 10 to the power of. So we have a proton concentration of 10 molar. Ooh. Oh, the pH equals -1. Oh, that obviously throws it a little bit, because people told me that the pH range goes from 0 to 14. Well, actually, these numbers here are not entirely correct. It can be from negative infinity to positive infinity, theoretically. There's no reason why it should stop at 0 or end in 14. So a pH of -1 is perfectly acceptable. It's just a pH, and it indicates that we've got a concentration of 10 molar of protons in our solution. Well, I am terribly sorry, Edith, that they lied to you, because you can very easily produce a 10 molar solution of hydrochloric acid. And actually, I think we are going to use one in one of the practicals. So it's not a problem at all. 10 molar just means 10 mole per liter of protons. Whether you want to call it hyperacidic or not, well, it's just acidic on the acidic range, right? Right. Now I've got a pH of 3.5. What is the proton concentration? Is a pH of 3.5 acidic or basic? Absolutely, a pH can be higher than 14 as well. It's acidic, absolutely right. So how do we do that? Now we know that pH equals negative log of the proton concentration. So the first thing that we do is we bring the negative sign to the other side. So what we have then is negative pH equals log of the proton concentration and, or I write it the other way around, log proton concentration equals negative pH. And what I now need to do is get rid of this log. And I should say probably log 10, but I'm just simply too lazy to write this 10 because everybody knows that it's the 10. What is the inverse operation of a logarithm? What's the inverse operation of a logarithm? Of the logarithm to the base of 10, I should say. Exactly, it is 10 to the power of. E is only for the natural logarithm. For the log 10 is 10 to the power of. So we have 10 to the power of log 10 proton concentration. And we have to do that with both sides of the equation. So it's 10 to the power of negative pH. So on the left-hand side, the 10 and the log cancel out, and we have the proton concentration here equals 10 to the negative of the pH. So this is how you can convert pH into a proton concentration and a proton concentration into pH. So again, make it aesthetically pleasing. So let's do it this one here. So that's the pH is negative log proton concentration, and the proton concentration is 10 to the power of negative pH. So we can do that for our 3.5 here. So what we can do is we can do 10 to the power of negative 3.5. And we got what people said. (3.16) times 10 to the minus 4. So here the proton concentration equals 3.16 times 10 to the minus 4. What's the unit? Absolutely right, guys. I'm very proud of you. The unit is molar. Yeah, it's always molar. So we've converted that, right? Excellent stuff. Now let's have a look. And I've set, or mole per liter, or mole decimeter to the minus 3. Whatever you fancy, as long as it's the right one, I'm very happy with whatever you want to write. So you've seen how we can convert proton and pH into each other. Let's also quickly have a look at some nomenclature. HCl, and let's stick with that, gives us H plus Cl minus, right? And we said this here is an acid, correct? Are you happy with that? We can also write this the other way around in this direction. Cl minus plus H plus gives HCl. What is Cl minus? What is this chloride? Strictly speaking, what is the chloride in this case? It's the base. It's an ion, but it's the base. Why is it the base? Because it is a proton acceptor. It's a proton acceptor, right? So it is the base. And Vernon used the expression conjugate. And the conjugate actually means we have an acid-base combination which differs only by one, that's important, by one proton. So if we look at HCl and Cl minus, HCl and Cl minus, this one is the acid, this one is the base, and the difference between the acid and the base is just one proton. Does that make sense? What about the following? NH4 plus and NH3. Which one could donate a proton and therefore is the acid? Which one of those is? So people say this one here is the acid. Absolutely right. And the NH3 therefore would be the base. Yeah? So we would have NH4 plus would donate the proton, and we get the NH3. Is this a conjugate pair? Is it a conjugate acid-base pair? Well, we have an acid and a base, acid and base. They are both the same compounds, but they differ by only one. Differ by one proton. That's the only difference between the acid and the base. Only one proton. So therefore, yes, it's conjugate base pair. Conjugate acid base pair. Yeah, does that help? Does that sound reasonable? Okay, let's have the pair. Oh yes, let's do a funny one. HOH, H plus plus OH minus. Is HOH or H2O and OH minus, is that a conjugate acid-base pair? Yes, it would be in equilibrium. Is this H2O and OH minus an acid-base, conjugate acid-base pair? So which one is the acid in this case? Which one is the acid? H2O, so that's the acid. What's the OH minus? Oh, the OH minus is the proton acceptor because it can accept the proton. So the OH minus is the base. So what's the difference between them? Acid and base. How many protons is the difference? We have one proton difference between them. And therefore, the answer is yes, it's a conjugate acid-base pair. It is a conjugate base pair. Okay, here we've got, what about H2O and H3O plus? H2O and H3O plus. Is it conjugate base pair? Yes, you're absolutely right. That's the acid. That's the base. The difference is one proton, so it's a conjugate acid-base pair. Absolutely right. What about O2 minus and H2O and OH minus? Ha, let's do it this way. O2 minus and HO minus. Is it conjugate? Which one is the acid in this case? Which one could give off a proton? Ho, ho, ho. Absolutely right. OH minus in this case is the acid because it can give off the proton and turn into OH or into the O2 minus, so that would be the base. Absolutely right. Is it conjugate? Absolutely. It's a conjugate base pair. What about this one? O2 minus and H2O. Which one is the acid? It's the water. Yep, you got it. That's the acid. And therefore the O2 minus is the base. Is it conjugate? What's the difference between the H2O and O2 minus? In terms of, it's 2 protons difference. And if it is 2 protons difference, it is not conjugate. So not conjugate base pair. Because of the two protons. So this is not a conjugate base pair. Make sense? So let's say we have water. And water can do H2 plus OH minus. By the way, what is the pH of water? So pH of H2O. It's 7. Yeah, absolutely right. So we have a pH of 7. Actually, what is the proton concentration in water? What's the proton concentration of water? No, Kami, I'm afraid that's not correct. No. None of you is right. Yes, thank you. It's 1 times 10 to the minus 7 mole per liter. Units, units, thank you. Absolutely right. Right? 10 to the minus 7 mole per liter. What is actually the hydroxide concentration of water? Can we do that as well? Well, let's think about it. For each proton that we have in water, in pure water, we have the same amount of OH minus of hydroxide. And Conrad is absolutely right. The proton concentration is the same as the hydroxide concentration. So that is 1 times 10 to the minus 7 mole per liter. And actually, what we could do really is we could also define something that's called a pOH. pOH of water is nothing else but the negative log of the OH minus concentration. So in this case of water, it would be pOH is also 7 in water. Absolutely. So how do actually pOH and pH actually how they relate to each other? And that's very easy, and I will show you that tomorrow. There is a very easy relationship. pH plus pOH together gives 14 in water. So I can easily calculate if I've got a substance with that, if we have, let's say, 0.1 molar protons in water. What is the pH? And what is the pOH? Well, the pH is the negative logarithm of that. So the pH for 0.1 molar hydrochloric acid, we've done that before. What was that? pH of a 0.1 molar proton concentration. That was 1. Absolutely right. And therefore, the pOH is, what's the pOH? 13. Absolutely right. You're totally nailing it. Okay, so we have done that. By the way, 0.1 molar hydrochloric acid, is that acidic or basic? It's very acidic. Now, usually we don't know the proton concentration of something, but what we usually know is the concentration of the, let's say, the acid. That is what we usually know. We don't know necessarily what the proton concentration is, but we know the concentration of the acid. So for example, if we've got a 0.1 molar hydrochloric acid, which is a very strong acid, in the hydrochloric acid, almost all of the hydrochloric acid dissociates into proton plus Cl minus. So if I start with a 0.1 molar hydrochloric acid, I will end up with close to 0.1 molar H plus 0.1 molar chlorides, because the acid almost totally dissociates. That is a strong acid. And if I can have 5 more minutes of your time, please, or do you have another lecture now? Do you have another lecture? No? Can I have 5 more minutes, please? Fantastic. So let's quickly say we have 0.01 molar hydrochloric acid solution. Yeah? How much protons do I have in this case? What is my proton concentration? Absolutely right. It is 0.01 molar. What is my chloride concentration in this case? I write this like that. Is it the same? Same. Yep, absolutely right. So, if we've got a very strong acid, we just simply say our proton concentration is the same as the concentration of the acid. And we will see tomorrow when we are discussing weak acids that this is not always the case. But if it is a strong acid, we have this relationship. So what is the pH? What is the pH of a 0.01 molar hydrochloric acid? 2. You are absolutely right. pH equals 2. So because it is negative log of the proton concentration, and I said the proton concentration is the same as the HCl concentration in this case. Okay? pH, is it acid or basic? It's acidic. Excellent. Okay, we have 1 times 10 to the minus 5 molar hydrochloric acid solution. Okay? What is the proton concentration? One times 10 to the minus 1 times 10 to the minus 5 molar. Thank you. 1 times 10 to the minus 5 molar. What would be the pH? Five. It looks like you totally nailed it. Fantastic. What's the pOH? Yep. Excellent. Well done. You got it? Doesn't cause you any problems? Okay. And now I'm going to F with your mind. Are you ready for that? Absolutely right. pH plus pOH is always 14. Right. You are prepared. 10 to the minus 5 molar hydrochloric acid. Is it acidic or basic? Acidic or basic? Acidic. Because we added an acid here, right? We added an acid. Right. I have a 1 nanomolar hydrochloric acid. 1 nanomolar hydrochloric acid. What is the pH? Katie says 9. 6. Oh, that's interesting. 6. Okay, nano means 1 times 10 to the minus 9 molar hydrochloric acid. 9. Okay. 9. Excellent. Excellent. It's not terribly difficult, is it? This calculation? Pretty straightforward. So it's 9. Is it acidic or basic? pH 9. So you're absolutely right. pH of 9 is basic. Do you see a little problem that I have here? No, we don't need to worry about the temperature. Do you see a problem? No, it is still an Arrhenius acid. Yes, Luke. HCl is always an acid. But we just calculated the pH, and you said it's basic. Do you see the problem? We have an acid, and all of a sudden the pH is basic. It's above neutral. The pH is now basic. You add an acid, and you say the result is basic. It's like me turning, water into wine. I know there was a dude 2000 years ago who could do that, but for me, it's usually the other way around. I can turn wine into water, but not the other way around. Do you see the problem that we have? We have an acid, and we calculate that the pH is basic. So surely this cannot be right. There is somewhere is a flaw in it. And here it comes. Here is the explanation what is going on. No, you don't need to use Ka or something like that, whatever this might be. Here is the explanation why we get this really strange result. It has everything to do with, I will explain tomorrow. Have a lovely afternoon or day, and I shall see you tomorrow for the explanation what's going on here. I shall see you tomorrow and try to figure out why we get this weird result. Enjoy and have fun, and look at your pH, pOH. There are lots and lots of practice questions that you can use on this practice calculation website. See you tomorrow, and thank you very much for watching.